Hey robot makers, hope you're having a good day so far. So do you want to make a Halloween spider lantern animatronic robot thing? Then this is the show for you. So let's dive straight in. My name's Kevin, come with me as we build robots, bring them to life with code and have a whole load of fun along the way. Okay, let me get over to Keynote and let me make sure I have Do Not Disturb switched on. There we go. There we go. Cool. So yes, this is about building a Halloween spider robot. So the inspiration for this was a couple of different areas. I saw this really cool design online and I thought I could probably reproduce that in Fusion 360. So that's something I have done. And I was thinking about what could I do to make this quite static design more robotic, more animatronic and maybe more interactive. So I'll show you a couple of the inspirations for that on the next slide actually. Now, tools and materials, so I've used a laser cutter to produce this. I've got some of the blanks just down here. These are the results. There's quite a bit of spare material on this, so I'm probably not going to throw this away just yet, but you can see there, that's kind of how I made the body of this particular lantern. I've used some basswood, that's that really lightweight, I think it's 2mm thick, just for interest. And I've also used a 3D printer, so I've just used a bit of filament and I've painted this black as well. Well, Jenny painted it black. So you can see on that picture just on the right there, it's come out quite well, the colour of it. You can see the wood grain and it's got this sort of nice, almost like a 1990s hi-fi black to it. So I designed all this in Fusion 360 and we'll have a look at that design in a minute or two. And it's what we're shooting for is a Halloween animatronic that reacts to a person nearby using an ultrasonic rangefinder. You can see there the sort of eyes of the spider are this ultrasonic rangefinder. So if you move your arm in front of it or you come closer to have a look, its arms will move open and close depending on the distance that you are. And for bonus points, we can also change the colour of the lantern inside. It'll be some RGB LED strips that we can change there. So this is the inspiration for some of the mechanics inside. So the Wi-Fi scanner mechanism I created, that Ghostbusters Wi-Fi scanner, had a really nice mechanism inside for when the sort of arms move up. There's an interlocking cog. So there's two arms, they mesh in the middle, and you only need to drive one of them with a servo and the other one will follow along just because of the interlocking mesh. And then the spooky, scary skeleton, that's got that nice mechanism for where if you wave your hand in front of it or you come closer to it, the servo will make the eyes and the eyebrows raise and the mouth open. And it's quite a dramatic effect on that one. And you can see on the right hand side there, that's the kind of design that I was inspired by. So rather than paying the £3 to download the design, I thought I can do that. I can spend all afternoon designing that, but then I've got the files and I can modify it the way that I want. Cool, so this is the spider lamp itself. I've got it next to me on the desk. I can show you that in a bit more detail in a second, but here it is, nicely painted black. You can see on the Fusion 360 design there on the screen. So it's got rangefinder for eyes. That little silver thing is just a little crystal that helps the rangefinder do its timing very accurately. You just need to allow space on the laser cut for that to push through. The front arms are based will open and close based on the distance that you are from that ultrasonic rangefinder. The servo will power those arms, it will make them move, just one servo. And it's all going to be MicroPython powered because I've got most of the code written already for that from various other projects that we've just seen on the other slide. So the web side panels, yes, I'm a web developer now, I can create all kinds of spider webs. These are laser cut as well. One of the really nice features of a laser cutter is this intricate design that you can create very easily, and the results are just fascinating. So you can see there we've got this really nice web effect, and that was simply me just doing some very simple lines and then manually putting a 3-point arc between them and just tweaking it so it looked quite organic. And then the laser cutter did its thing, only took it about 40 minutes I think to do all 6 panels. That's because I've got a 5-watt laser cutter, it's quite slow. So yeah, really nice for cutting out intricate patterns and quicker than 3D printing. So to 3D print 6 panels with that amount of detail in them and them not have loads of problems afterwards because 3D printing has its issues as well. I think this is a really good use and you can see how sharp those panels are as well, how nice and accurate they are. The cog mechanism, so this is something I really was looking forward to putting together. I've actually created that just next to me here. We can talk a bit more about this in a second. So let me just make sure this is all connected up. So if I just hold this up, you can see there's two interlocking cogs. I'm just holding them in place so they don't fall over there. And if you move one, it'll make the other one move with it. So you can see there, if we just move one of those, the other one will move at the same time. So that's the use of interlocking cogs. Now Fusion 360 does have a cog generator, but it's actually easier than you think to create these. So I simply just created my own tooth profile and then just rotated that design around at the central point of that cog, just using the circular pattern feature of Fusion 360. And then all I did was just offset. I basically just duplicated that cog, offset it ever so slightly so that rather than meshing, like overlapping, they were interwoven. You can also see there that there's various different circles on that design. We can have a look at the Fusion 360 design if you like in more detail. But you can see there's a sort of inner and outer circle for the cogs, and I purposely designed them so that they would design in place to definitely mesh nicely. You can also see there's a round bit there as well. You've got to make sure that that the cog doesn't go all the way to the bottom there, otherwise they'd have to be quite further apart. So there's quite a bit of a science to designing these teeth, but that was my very simple method there. So you can just see we've got like 0.75 of a millimeter, of a millimeter, and then 1 millimeter at the very bottom of that. And I think it's about 2 or 3 millimeters tall, I think, that as well. So there you go, that's how we put together the teeth mechanism and the mesh, and then we simply have a servo that's sat above that. So I've got this nice, let's show you on here. Most servos come with a little pack of servo horns. That's what these little plastic things are called. So you typically get a little bag full of all different types of servo horn. So you get like long ones, double ones, little 4-spoke ones, and you often get a circular one like this as well. So the idea would be we would simply glue this circular piece onto the top of one of those cogs. And then I need some kind of mechanism that I can push this into. So I've 3D printed a little part that you could push this into, and then the cog can be sort of on top of that. So that will then connect everything together. Now we'll talk about this design because this shouldn't have 2 parts to it. It should be a single piece. We'll talk about that in a second or two. So the rangefinder. So this can detect objects, people, anything in front of it, up to about, I would say, half a metre. We've got a good 60 centimetres probably depth on these typically. And this particular design, the code I'm using is based on the spooky scary skeleton that I designed a couple of years ago. So if you want to find that one, that's on the ideas page on kevsrobots.com. If you just click on the Halloween section, you'll find what you're looking for there. I think I called it bare bones, the code. It was a skeleton code. And you can see that this is what it's like in action. If I move towards it, it will react. So you can see its little eyebrows go up and its mouthpiece drops down. So I had this, so this you can see that on the screen there, this is a little, I think it was a TikTok or Instagram type thing that I made for showing you how this spooky scary skeleton actually works. So the rangefinder detects the person in front of it and then it triggers a reaction. So there's simply a piece of code that says if the distance is less than a certain value, say 30 centimeters, then trigger the event, whatever that event might be, or just drop into the next line of code. So yes, that's something that we can check for in our code very, very simply. Cool. So I'm going to show you that. So wiring wise, it's pretty straightforward to wire this up. So you need a HC-SR04 rangefinder. These are an ultrasonic rangefinder. They do come in 2 varieties. So there's a 3.3 volt version and there's a 5 volt version. And the way that you can tell on this, if you look on the back of the rangefinder, you'll see a couple of chips. Now if it mentions SDA or SCL on there, which is an I2C protocol, if you like, way of communicating, that means you've got the 3.3 volt version. If you've not got that, you've probably got the 5 volt version, and you'll need either a voltage divider or you'll just need to get the correct one. So definitely check out those and you've got the right one, and it'll work straight away on your microcontroller. I'm using a Raspberry Pi Pico on here. You can use I would recommend an Arduino ESP32 I think it's an Arduino Nano ESP32 like this one here. That's on this little board. They'll work just as well. Depends whatever you've got to hand. If it can run MicroPython and it's got a couple of pins on it, just need like 3 pins, then you're golden. So I've got a servo here. This one is a DS959MG. You can also use any SG90 type servo. It doesn't need to be particularly powerful. It just needs to take a simple signal pin on that. Now I think on this particular diagram I've got the signal for the servo going to the very bottom pin there. I think the way I've got it wired up on my desk, I'm actually using pin 2, which is like the third one down. It doesn't really matter as long as you've got those paired up in your code and on the physical device there. And I'm simply taking the 5 volts to power the servo from the top of the Pico there, and then to power the ultrasonic rangefinder I'm just taking the 3.3 volts, which is like the 5th pin down on the right there. So there we go, that's how we can wire this up. It's pretty straightforward, and we're just taking the trigger and the echo pins from the rangefinder into pin 0 and pin 1 on there as well. So if you like what I do and you want to help me grow this channel, please give this video a like, drop me a comment to let me know if you've making any particular projects for Halloween, and if you've not subscribed, please consider subscribing. It means an awful lot to me and it helps grow the channel as well. I do go live every single Sunday, sometimes twice because the stream seems to drop. Hopefully we'll get to the bottom of that very soon, but it has been happening for I think the past 6 weeks now, which is quite frustrating. Anyways, so here's the code that we've been working on for this particular rangefinder. I think this code I've shared previously. It's on the Bare Bones, which is the skeleton, spooky scary skeleton project as well. And you can see that it's a class. That means we can have our variables and our functions all in the same object. Makes it easier and tidier to manage. And you can see there we've got a duration and a distance. So the duration is going to be how long it takes for the signal to bounce back and come back to the receiver. And the distance is a calculation that we can do, and it's in that code there. It's at line 36. So what that distance calculation is it's the speed of sound times the amount of distance times the duration, how long it's taken the signal to bounce off whatever, divided by 2, because it's going to bounce off and it's going to come back. So we just need to have that. So that's how we calculate the distance. And the way to make this work with one of these ultrasonic rangefinders is we simply set the pin to be low to begin with. We sleep for an amount of time, say 2 milliseconds, microseconds, whatever. We then trigger it high, and then we wait for 5 US, then we trigger it low, and then we can take the time. So by doing that, we will have fired out that signal. We can then say while the value is 0, so while nothing's happening, increase the ticks that's in signal off. Ticks is how long the microcontroller has been up, how long it's been switched on for in microseconds. I keep saying microseconds. I'm not sure if it's milliseconds or microseconds. I'm going to stick with microseconds for now because I think it's ms for milliseconds. Once it's received the signal back, it's bounced back off something, we can take another time, which is the signal on time, and then the distance is the signal on minus the signal off, and then we can then work out what that actual distance is by just doing that, timesing it by the speed of sound, dividing it by 2. Whew. So this is the rangefinder itself. You can see there it's got a voltage in, a ground pin, and it has a trigger and an echo pin. So I think they're actually on the wrong ones there. If you look at the diagram there, so the VCC is correct. The very end one is actually ground, and the trigger and the echo are the middle two. I'm not sure. I need to update that one there. So yeah, be sure to buy the 3.3 volt ones, not the 5 volt ones. It makes your life a lot easier. And then this is how it works, kind of from a physics point of view. So if we say we've got a distance of 30 centimeters there, we send out our ping. It bounces off an object, and it's traveling at 3,440 centimeters per second, and the time it takes to hit that. I'll just run that one again, actually. Sorry. There we go. So yeah, the sound wave is traveling at the speed of sound, 3,440 centimeters per second, hits the object. The time to the object is 17.64 microseconds. So we divide that by 2 milliseconds. Divide that by 2 to get 8.882 milliseconds, and then if we times that by the speed of sound, we will get the 30 centimeters if you round that number up to the object. So it's pretty accurate. It's good enough for what we need, which is just detecting people and things in front of it. So for the Arduino ESP32 or Raspberry Pi Pico, we can use any of these really in our code. They're both going to run MicroPython and interact with the pins in the same way. So to get the distance from the ultrasonic rangefinder, we need to write a block of code for that. That's our rangefinder code that we looked at a couple of seconds ago. We then need to move the servo based on some kind of starting point. So what I will want to happen, I just grab my little robot legs here. They can either be legs or... Yes, I did drop something then. They can either be legs, or they can be like mandibles, perhaps, if it's a beetle, whatever you choose. So they're going to have some kind of starting point. So maybe like they start out like this, and then the closer you get, the more they might move together. Or they might start like really far apart like that, and then the closer you get, the more they'll get. But there'll be a point where we want them to stop. I mean, these potentially could cross over, but really they should sort of stop in the middle like that. There'll be some kind of default position that we want them to stay in. So we need to figure out what that default position is in angles on our servo, what the maximum position is that it'll open to, and what the minimum position is that it can close to. So we just need to have those kind of 3 values there. And what we need to do is map distance to the angles. And it's really easy to do this with a map function. So we can create a map function that will do that for us. And then the simple logic will be, if it's greater than 30 centimeters, just move back to that default position where the hands are kind of open. If somebody comes in within 30 centimeters, make them start to close, depending on what that distance is. So we'll have a look at this. So this project has gone a little bit wrong, and I want to show you, I thought this was kind of worth sharing as a teachable moment. So a couple of things that happened. The little servo holder that I created was too weak. The parts needed to be much thicker and stronger. And when I designed this in Fusion 360, you often don't get that kind of feel for how weak or strong something will be. So it's a mistake I continually make with things. As soon as I was putting this together and even just pulling off some of the support material, it just split in two, because it's not strong in that kind of where the layers overlap. That's the weakest kind of part of a 3D print. The panel pieces, they also need to be slightly better joined together. So these are quite delicate. They're simply held in place by, there's a little tab. Let me see if I can get that into the camera. There's a little tab, and that tab is pushing into just a little tab recess on this ring here. And it means there isn't a lot of surface area for the glue to grab hold of. So I'm pretty sure that these will pop out or fall out if it's handled in any kind of rough way. So if somebody like smacks the spider, it might all just sort of fall apart, if you like. Similar with these other pieces that go around as well. They're sort of just friction fit, grabbing hold there. And the idea is that the rangefinder piece, if I just go to the overhead for a second, if I put the spider down like so, this piece, it's got some little spacers on the back, and that will simply just glue into place on there, so the spider looks nice and neat. And then on the other side, this is where I would glue, let's get that about right, I would glue these sort of mandible pieces. The servo will glue to one of them, like so. Let's see if I get that into the right way around. I think I've put this in the wrong way around. There we go. So if that's there, the servo goes that way round. Little servo horn can be glued to the back of there. And the idea is that kind of holds everything together like so. And that would be just on the underside. So this piece would be glued on the underside of these here, like so. So the mechanism would be on the other side of that, like there. And this would be on the top. And then we would have the microcontroller just somewhere, either inside the lantern or around the back, something like that. So the panel pieces need to be a bit stronger, and the cogs currently can sort of jump out, so we need something to hold them in place as well. Again, this is my first time really working on a proper project with laser cut pieces, and it's kind of a different mindset than a 3D print, and I thought I would try and use the minimal amount of 3D prints on this so that it was more of a laser cut project. So there are a couple of things that I need to work on to make this better. So I'll do that as a part 2 to this particular project. And learning through your mistakes, this is how you learn. So you often you often don't see the mistake until after you've made it. And that's a really frustrating thing. Like, why didn't I see that those 3D printed parts were too weak? It's because I hadn't anticipated that. And sometimes you might be working in millimeters, but only when you print it out do you realize how physically small and fragile that is. So you might need to go back, and you'll probably not make that mistake again because of the amount of effort it takes, time it takes to build these things. So it's just something that you learn only after you've made the mistake. So you need to embrace that when that happens. It's just part of the learning process. It is a bit frustrating, but it is something that does happen. And you need to think about different ways to solve the problem. So what do you need to know to solve this problem? It might be that you don't need to know anything. You realise from the mistake that it's obvious you need a stronger part or more glue or whatever to make this happen. You might need to know who do you need to ask, or where can you find that particular information from? Is there somebody else who is more experienced in this that can kind of just say it's obvious you need to do this instead? You can think about other things you could try instead. So maybe there's a different technique, or you can not use 3D prints, you might use something else. Just entirely make this out of laser cut parts, for example. And sometimes a whole redesign is required. Now, sometimes what I also will do is I will open up a fresh Fusion 360 project. I'll start working on a project knowing that this isn't going to be the one that I finish with. This is just part of the process of learning, how big the parts need to be, how they fit together. And then I might make a second file, which is kind of a cleaner design, one that's got all the mistakes kind of cut out and just works. So sometimes a redesign is required. So let's have a look at the code that I've written so far and have a play with this, shall we? So I'm just going to load up Thonny over here. I'm also going to get this on the screen so that we can see the rangefinder there. I've simply just got, I'm just going to show you on the screen there, I've simply got, this is a Pimoroni Pico Explorer. I love this little thing. It means you can just plug in wires and have things just work. So I've got this rangefinder here, and I've got some code. So let's have a look at what the code is doing. So I'm just going to go full screen so we can look at this. So this MicroPython is actually Pimoroni MicroPython, and they've got some nice helper functions for things like servos in there. So you can see where I've got from servo import servo. That's the Pimoroni MicroPython firmware. You can install this from Thonny just by going down here, clicking on the configure. When you go to install MicroPython update, you can actually choose what family of MicroPython that you actually want to install and what variant. So if I go down here, you can install the Raspberry Pi Pico WH with Pimoroni libraries, and that's simply what I've done for this particular board. So that's where we get that from. Time sleep, they're pretty standard things to import there. Rangefinder is the one I've created earlier, so that's the class that we looked at before, which simply has a duration and distance variable inside the class. So we can do whatever we call this dot distance or dot duration. We pass in an echo and trigger pin, because depending on which we use for our projects, this makes it much more reusable. And then we've simply got a ping function. So ping will ping out to the object that's in front of it, and it will pass back the distance. It will return the distance. So that's what the rangefinder code will be. We do need to copy that down, so you will typically need to do upload to and have that on your Pico device. Or if it's the Arduino, you need to copy it there too. And what else do we need to do on here? So that is the rangefinder. The servo models the servo itself. You can just pass in values and it'll go to that particular angle, which is nice. And the math, that was me just playing around with some rounding functions, so you can import that if you want to, but I don't think we use it on this particular code. We've got 3 pins that we need to take notice of. So there's the echo pin, the trigger pin, and the servo pin. So on the diagram before, I think I had that as like pin 16 or something, but on this one it's pin 2. That's what I've got on there. These are all uppercase because they're constants and their values are not going to change throughout the life of the code. We might just change them if we plug it into a different pin, for example. We've then got these different positions. So we need a default position. So I've set this to the angle of 0. The maximum position I want is 90. Then there's a minimum distance that we want things to trigger to, and a maximum distance where we don't care what happens after that. So we've got those 2 there as well. We'll use them in a minute in our map function. We then create a servo object. So it's probably best to call that something other than servo, since as we're importing servo. But for this, it's probably not too bad. We could probably just call that like S1 or something like that. or servo 1 would probably be a better name. And then the rangefinder, that's just going to take in our rangefinder class. We're going to pass in the echo pin that we defined there, the trigger pin, and then it'll be ready to use. We can do rangefinder.ping and it'll pass back that distance. So this map function, this is used quite a bit whenever you want to take a range of values. Say you're working, well, in our case, we're working from distance, and we want to change that to be the angle that we're moving our servo to, and we've got a current value, so a current distance value. So we want the minimum and maximum values, which is the distance ones, for example, and then we've got the minimum and maximum angle values that we want to be working with, and this will scale that value to be the correct value that we want to find. So it's simply going to take that ratio. It's going to take the current value from the minimum, divide it by the maximum from the minimum, and then it's going to say the map value is the 2 minimum plus the ratio times the 2 minus 2 max to min, and then it'll return that mapped value. It's one of those that if you play with it, it really works well. It's one of those sort of magical functions. The get distance is simply going to grab the distance from our rangefinder, so it's going to do rangefinder.ping. I'm dividing this by 10 because the values I was getting back from that were in millimeters and I wanted centimeters, and I've rounded this up because it gives you like a whole bunch of floating point numbers to just 2 decimal points. So you can see there it's running and it's currently giving us a distance. If I stick my hand in front of this, you can see it will drop right down. If I move my hand away, it will stop again. We've got this move to default position. So this is when it isn't detecting anything in front of it, we want the arms to move back to that position, and we've defined what angle that is at the top there. That's just going to be like angle 0. And then we've got this move to distance. So whatever the distance value is, we're going to move the angle depending on what that is. And this is where our map function comes in. So we can say we want the angle to be an integer, a whole number, and we say we're going to map the current distance value between the minimum and maximum distance and the default position and the maximum position, which is our angles. And then we're going to print out distance moving to angle. So if I put my hand in front of this and move down, we can see there the closer I get, the lower the angle is going to get, and the more I move away, the higher the angle will get as well. We could change that if we wanted to, simply by just swapping around the max and min values. That would work just as well. And then we just set to the value of the angle of the servo, just doing this servo.value and passing in the angle that we've just defined there. And then the main loop is simply just, while true, get the current distance. If the distance is greater than 30 centimeters, then move to the default position. Otherwise, move to the distance that you've just read in, and then just sleep for a quarter of a second. So that's what we can see working there. So if I now go back to this overhead thing, and the more I put my hand closer to that, if I just make this more in the middle of the screen. So if I move my hand away and then move it closer, you can see the distance is getting less and less and less. And the angle is also changing. The more I move back, it'll go back to a higher angle. So if it's above 30, you can see there that it's not going to do anything. It's only when it gets below 30 that it starts saying it's going to move the servo. I think I must have blown up these servos because I tried getting this to work just to demonstrate this on the stream today, and that didn't work either. So double disaster there. But you can see the code's working fine there as well. Cool. So let's get back to over here. So if you want to get yourself one of these amazing merch hats, you can do. They're on the kevrobots.com/merch. These are the Robot Maker hats. They're in a range of colours. I might get a winter one, perhaps, just to mix things up a bit. I did have a red one, but I think they look a bit too much like those MAGA hats in the US. And I know that at least half the audience won't like that, so I decided to go for a neutral colour such as black. So there we go. And if you're not on Discord, you can join our Discord server. If you go to kevrobots.com/Discord, you'll find a really nice community of people there. A couple of thousand people on there, I believe now. It's really growing rapidly. And if you follow me on social media, I'm on all the social platforms. I'm on Threads at KevMcAleer at threads.net. On TikTok, I'm at KevMcAleer6. On Instagram, I'm at KevMcAleer. On X, I'm at KevsMac. On Mastodon, I'm at kevsmac at mastodon.social, and on Blue Sky at kevsmac.psky.social as well. And if you want to join me, you can get your name in the end credits simply by going to kesrobots.com/coffee, and you can get your name in the credits like other people are going to do in a second. So let's do that now, shall we? So we have a number of people who've been supporting the show. So on the left-hand side here, Johnny Wilson bought me a coffee. Thank you so much for that, Johnny. Really do appreciate it. And we had Andy Brooker join last week as well as a new member. We've also got Shemi, Alvaro, Marie, Jeff, Steve, Deanne Corty, Marlene and Tom on the Buy Me a Coffee side. And then on the YouTube side, we've got Bello, we have Orcsred39 at Littleback, we've got Paul, we've got Johnny, we've got Hans from Cheerlights, Stephen, we've got John Paul, Alistair, Cassie, Tinkering, Rocks, Johnny and Michael, and of course we have Tom. So thank you so much for that. If you want to get your name in the credits, go to kesrobots.com/coffee or kesrobots.com/credits to get yourself in the Robot Overlord army. Cool. So there we go. That's the why does that look shrunken on there then? That doesn't look quite like it should be the right side. Let me just maneuver that back there. Just moving around an overlay that you can't see but I can see. There we go. Cool. So what are we? I think that is everything on the main show today. Yes, it is. So at this point in the video, YouTube will recommend over here another video that it thinks you should watch. Please consider giving that a watch. The more that you binge watch my content, the more that YouTube will suggest that to other people as well and help the channel grow in general. So yes, I'm hoping to get to the bottom of that technical issue that keeps happening every week where we see the stream seems to split into two, and it always seems to be okay after the second part. It never splits into three, so I'm not sure what's going on there. It's quite frustrating. But there's a whole stack of technology that I'm using to broadcast this out today. Could be any one of those things, and we're trying to isolate each one each week. So hopefully we'll get to the bottom of that soon. So yes, it's at this part of the video I'll say thank you so much for watching, and I shall see you next time.